Assalamu alaikum. So far, we have discussed most of the power electronic devices and their circuits, but there are some technical challenges whenever we want to turn these devices into a practical application. Some of these practical considerations that are yet to be discovered are the gate driver circuits, the stubber circuits, and the requirement of the heat sinks to enhance the power handling capability of a device. So let us start with the concept of the gate driver circuits. Why the requirement of gate driver circuit is necessary for the good implementation of a power electronic circuit. So suppose that we have a microcontroller system here. This microcontroller system is connected the with the power switch. This power switch could be a BJT, it could be an IGBT, and it could be a MOSFET. In order to understand the concept here, we need to understand that if a microcontroller or any other digital signal processing board or FPGA kit is connected directly with the power switch, then there are certain limitations which will not allow the power switch to turn on and off at the required switching frequencies. What are these requirements? That we are going to discuss in this today's lecture. So a power switch, if I talk about this, let me draw a MOSFET. This MOSFET is a voltage control device, which means if the voltage applied on the gate to source, this voltage VGS, if it exceeds a threshold voltage, which is usually given on the data sheet, then the device moves into the conduction mode. However, there are junction capacitances here. For example, we have a junction capacitance between the gate and the source, which is known as the CGS. Then we have a junction capacitance between the gate and the drain. And then we have the junction capacitance between the drain and the source. Among these three capacitances, the input capacitance consists of the gate to drain capacitance and the gate to source capacitance. In order to keep the device on, we need to charge this CGS to a value where the device stays in a conduction mode. And in order to turn this device off, we need to discharge the input capacitances so that the net voltage across the gate to source terminal become equal to 0. Now, the amount of charging and discharging depends on the amount of current that flows from the circuit into the power semiconductor switch. Now, this C in is something which defines the maximum frequency at which a device can switch. So, if we charge it faster, means that the device turning on is fast. Similarly, if we discharge this at a faster rate, then the turn off of the device becomes fast. So remember that whenever we are using a device, it either is operating into the saturation region or into the cutoff region. And the transition from the saturation region or the on state to the off state, it is not something that it jumps from this on state and off state. Rather, it has to cross this region which is known as the linear region. The shorter a device stays into this linear region or the active region, shorter we have the power losses across a given device. And therefore, it is imperative to have a switching speed fast enough so that the device traverses at a very small portion of time when it is switching from the turn on position to the turn off position. And this is where the problem with the direct control of the power semiconductor device with the microcontroller occurs. So here we can see here that if we have the microcontroller connected directly with some power switch, for example, say the MOSFET, then the amount of current which is required to charge the input capacitance, which is this capacitance connected between the gate and the source, that capacitance requires some amount of current to charge at a higher rate. However, with the direct application of a microcontroller with the power switch, this microcontroller has a limited fan out capability, which means that the amount of current it can provide to this switch is limited, and therefore, despite the fact that a microcontroller is able to work at a very high frequencies, it may not be able to turn on and off the power semiconductor switch effectively at the desired rate. This is the first problem by if we talk about the direct connection of this microcontroller with the switch. The second problem here is that in most of the power semiconductor devices applications, this power switch is connected on to a high power region where we have substantially higher voltages and higher currents, whereas this microcontroller is usually limited to something between 3 to 5 volts, and at a few milliampere current is the requirement for this microcontroller. And because the power semiconductor switches are used to control the flow of power from one side to another side, there is a lot of magnetics involved in the actual circuitry of a converter, and on top of that we have the inductive and the capacitive behaviors in all the real life systems. Therefore, it might happen that if we have any, for example, we have a voltage spike occurring on to the power switch side, it may be transferred onto this microcontroller, and therefore it can damage the controller itself. And therefore, the direct connection of this microcontroller is not a solution in a power electronic circuit. We tackle this particular problem by something which is known as a gate driver circuits. So gate driver circuit is actually a kind of a circuit where we where we have an interface between the microcontroller board, and here we have this switch here. So let me draw the switch. So here we have the switch. So this switch could be anything. It could be a BJT, it could be a MOSFET, but for all kind of interfacing between the controller and the switches, we add another block here that is known as the gate driver circuit. Now, the gate driver circuit receives the input from a microcontroller, and then it drives the switch according to the instructions provided by this controller board. So the properties of gate driver circuits are very important, and the topologies and the types of the gate driver circuit greatly depends on the type of a device that is to be driven by a given gate driver circuit. For example, if we are using a BJT, then we require to have a gate driver circuit which is capable of providing substantial amount of the base current to turn this BJT on. Whereas for the MOSFET or for the IGBT, where the main requirement is to have a voltage shift in the input voltage, we require to have something around 15 to 20 volt to turn the device into a deep saturation region, and we also need to have some substantial amount of current to charge and discharge the input capacitance of these particular devices. So based on the type of the device, the gate driver circuit can vary. Further to this, the topology, so the first thing here is that the gate driver circuit, it depends on the power switch. This is the first thing. The second thing is it also depends on the location of the switch. So there are two broader classification of the switches when they are connected onto when they are connected in a given power electronic circuit. So let me draw two circuits. The first circuit is that of a buck converter. So okay, let me draw a generic circuit here. It is that of a buck converter. So here we have the So this is the complete buck circuit. And the other one is known as a boost converter. Let me draw that as well. So for a boost converter, we have inductor on the input side. Here we have the switch, and this is the buck converter. So here we have, this is the boost converter, and here we have the buck converter. Now, if you notice here that we can have a control switch for a boost converter here, and for a buck converter we have the switch is connected here. So just to be fair, if we notice here that if I replace this switch by some IGBT or by some MOSFET, for example, let me take the MOSFET here, then we have this is the drain, this is the source, and here we have the gate. So if I replace this switch by this switch S1 on a buck converter, we notice that the source is not connected with the ground. Whereas for a boost converter, if we replace the switch S1 with that of this MOSFET, then this source is connected with the ground terminal. So this provides us another classification of a gate driver circuit with respect to the position of the switch that we want to control. So all the circuits where the emitters or the source is floating or it is not connected with the ground terminal, those type of circuits are known as the high side switches. So here we have this high side switch, and here we have a system where we have a low side switch. Now there are some technical issues that arises when we have a switch connected on the high side, and this low side driver circuit is considered easy to operate, because to turn on this device we have to apply the gate to source voltage where this source is connected with the zero potential, and therefore there is no such thing to elevate the gate voltage such that we have a VGS greater than the V threshold values. Whereas for this circuit, this VGS, if we want to create it, if we want to make it greater than the V threshold, and then there are some certain challenges that occur, and that we will discuss when we will deal with the high side switch. So we will start the discussion on the gate driver circuit with the low side drivers. We will see certain options, how to build some circuits which are capable of deriving this MOSFET in an effective way. We will also see the gate driver circuits for the BJT as well, but in the first stage we will only discuss about the MOSFET. So let us start the topic with the low side driver. Okay, so for a low side driver, low side driver for MOSFET. So we all know that MOSFET is a majority carrier device, and it is a voltage control device. Therefore, if we want to turn on MOSFET, then the simple condition is that the VGS should be greater than or equal to the V threshold, which is usually 4 to 6 volt, and the maximum range of this VGS is confined between 10 to minus 20 to 20 volt. So for turning this off, the condition is very simple, that we have to bring this VGS less than the threshold value, and this threshold value is the bare minimum at which the transistor just turns on. The other consideration here are that in order to turn on the device, the C input, which is a sum of the CGS and CDS, they should be charged, and to turn it off, this C input, which is the CGS and the CDS, they need to be discharged. These are the two conditions that whenever we meet these two conditions, the device either turns on or the device goes into it goes into the blocking state. So now the first circuit here is that, let us say that we have, this is the load, and here we have the MOSFET. So let us connect it with some source here. Let us say this is some controller. We have to use this resistance to limit the amount of current, just to safeguard the amount of current that this device can handle. Now, in this particular condition that we have earlier discussed, that if it is connected directly with a controller, then it will not be able to switch effectively because of the amount of current that this controller can supply. Further to this, the important point that we missed earlier is that if this controller is not able to sync, if it is not able to sync, then we have to add another resistance, and which is in the form of here. We need to use this particular resistance R2. So here we have this R1 and here we have this R2. Now this R2 is only required to discharge this input capacitor CGD, which is the gate to CGS, which is the gate to the source capacitance. Remember that the other capacitance, which is this drain to source, it is not of very significant importance, although it do play a role in defining the turning on characteristics of a MOSFET. But right now, we need to discharge this capacitor effectively to turn off this MOSFET. And for that, we have installed another resistance, which is said to be equal to R2. Now, this R2 should be greater than or equal to 10 times the R1, because it is only used to discharge this capacitor once we have a load signal applied from this given controller. And this is usually required when the controller is not able to sync. That is, it is not able to take back the current which is due to the presence of the gate to source capacitance. So the first problem can be tackled out by using some logic IC. So for example, as an option number 1, we can use some logic gate IC. For example, let me use the 7404. It is a hex inverter or a NOT gate. So we have 6 NOT gates available here. Each of the NOT gate has its own output current capability, and therefore if we short all the inputs, all inputs are shorted, and we short all the outputs, then we can actually enhance the current I naught is into times 6 times we can enhance the current capability of a single NOT gate. But again, the problem is that for most of the time this is not a solution which is feasible, because it may not be able to suffice with the switching conditions, and therefore we require to have something which is able to level shift up the input voltage, so that the device can go deep into the saturation region. This logic IC is usually able to work at a value equal to plus minus 5 volt, and we have 2 pins, one is connected with plus 5 volt and the other one is grounded, and therefore it is not capable of stepping up the level shift. It is not able to shift the level up for the gate to the source voltage. So another option is to use a configuration which is known as the double emitter configuration or the totem pole configuration. Now the totem pole configuration says that for the same circuit we have, suppose this is the load, and we have to turn this on. So if this is VCC, we will use a pair of the NPN transistors and the PNP transistor, and these two are connected with another supply. Let us say it is VG. Let me say this is Q1 and this is Q2. So we apply the input voltage here. So here we have the train of pulses that are to be applied ultimately to this device under the testing condition or the device under operation. So here you can see that whenever we turn on the switch Q1, then we have a flow of current from this VG. Okay. So whenever we turn on the switch Q1, then we have a flow of current in this direction, and this will ultimately charge this capacitor at a required rate, at a required rate. So by turning on the switch Q1, if the input is high, this will be turned on, and it will charge the C input, and consequently it will turn on this device under test. If we have the low signal applied from the controller, somewhere here we have the microcontroller. For a low signal, the Q2 is turned on, and this Q2, when it will turn on, it will allow the flow of current from this CGD back from the input capacitance, and it will discharge the input capacitance through itself, and therefore Q2 is used to discharge the C input. So this particular configuration is known as the push-pull configuration as well, because here one transistor, which is the NPN transistor, it is pushing the current into the input capacitance, whereas this Q2 is used to pull out the capacitance, and therefore this configuration is known as the push-pull configuration, or sometimes we call this as the totem pole configuration, or sometimes we call it a double emitter follower configuration. So this is for the low side driver of the MOSFET. If we have a BJT and we want to control this BJT, or if we want to have an effective switching of a BJT which is having its emitter connected with the ground terminal. So let me draw here we have the load. Remember that the power BJT has a lower beta, so beta is quite low, and therefore it requires substantial IB to turn on. We can increase the switching speed of this BJT if, for example, we have in the initial time, for the initial turn on, we have an IB higher value, and thereafter we keep this IB at a lower value. This can be effectively done by introducing another resistance here. So instead of having single resistance, we can have the two resistances, and here we have one capacitor which is connected across this resistance. So this is R1, this is R2, and here we are applying the input voltage here. So here we have the IB that flows through the R1 and R2, and consequently become part of this transistor that we want to turn on. Now here you can see that when we have initially this capacitor C1 is discharged, and therefore the initial current which will flow through this capacitor shall have this R2 shorted by this capacitor C1, and therefore the current IB1 that will become equal to V input minus VBE divided by the resistance R1 only, and therefore for the first part of the switching scheme, a higher current is supplied by this circuit to this BJT, and therefore it will quickly turn itself on. Now once it is turned on, we want to reduce the amount of current, so this IB2 becomes equal to VI minus VBE, and that will become equal to R1 plus R2, because now this capacitor is now charged, and therefore it will not allow the current flow through itself, and therefore the current shall be flowing only through these series resistances R1 and R2. Now as a result of this arrangement, we have this type of the circuit where we have initially we have a higher base, let us say this is IB1, and thereafter the current IB2 flows through the entire operation, unless and until we have this switch in an on state condition. Now In order to cater for the first order transients that occurred because of this C1 and R2, we need to find out the time constant before we design this set of resistances R1, R2, and C1. And for that, the amount of time constant tau, that is equal to RC. Here we have two resistances, so that becomes equal to R equivalent into C, and therefore this tau is equal to, the R equivalent becomes equal to a parallel resistance R1 plus R2 divided by R1 plus R2 times the value of C. So we need to make sure that the system comes into a steady state value before we move on to this IB2. And therefore, depending on the amount of capacitance and the resistance, we can set the time constant such that the system comes into a steady state condition before we apply the before we make any changes into the circuit. Otherwise, if this 5-time constant is not maintained here, then we may not be able to achieve a steady state switching characteristics for this particular BJT. So during this turn off, this charge capacitor provides a negative current, and therefore negative gate current spike is applied onto the base current, and therefore the base charge is removed effectively and very quickly. We will go through the simulation of the circuits that we have discussed so far. There are a lot of circuits that are used to realize the low side driver switches of the BJT, IGBT, or for the MOSFET. But we will shortly discuss in the next lecture we will discuss about the ready-made integrated circuits that are dedicated and that are readily available for driving the high side or the low side. Till the next lecture, take care and Allah Hafiz.